Hello everyone, welcome back to the course. So in the last class we tried to gain an understanding of the hydrogen production from biomass, which essentially is going to take place through gasification route as of now. There are other pathways like anaerobic digestion which are gaining momentum, but as of now the gasification pathway is the primary one which has been given a lot of emphasis. And in this particular lecture we are trying to analyze like how does the economics entail for the production of hydrogen from biomass through the gasification route. So one of the biomass that we are going to take into account in this case is the corn stover. So what is a corn stover? So we all have had a sweet corn or tasted sweet corn or relished different kind of cuisines made of corn in the past. So this is what the corn looks like, and this is where it goes. It grows on a tree like this, and what you have, the remaining part of the tree, which are essentially the leaves, are called the stover. And this is a waste, doesn't have much of a value. So what we are emphasizing is like, can we use this corn stover in the areas which have a lot of corn production for the production of hydrogen. And this is something we are going to analyze in this case study that we are going to understand in this particular class. So what we are going to take is the production of 1 million tons per year of corn stover, and then this corn stover is going to have a composition which is given to you, and the composition could be understood in the terms of proximate and ultimate analysis. To start with the ultimate analysis, this is basically breaking down in terms of elements like carbon, hydrogen, oxygen, sulfur. So the typical corn stover would normally have 47% carbon, around 5.7% of hydrogen, oxygen a percentage slightly roughly around 40%, some amount of nitrogen less than 1%, less than 1% sulfur, a significant amount of ash which needs to be dealt carefully, and then we would also have a typical higher heating value which entails as well. And then we also need to understand the proximate analysis. So what is the proximate analysis? This is basically being used for the characterization of coal in the past, and now it is also used conveniently for the characterization of biomass. So then we have something called as fixed carbon. So that is going to remain as carbon if we are heating this biomass in no supply of air. So this is something that is going to be left behind. Volatile metals are basically the volatile compounds that are going to escape if when we are heating the biomass. So if we are heating this biomass, which is the corn stover, in without any oxidizing agent, roughly 60% of this weight of this biomass is going to escape as different gases, which could be different molecular weight gases. And this is where majority of the gases for a gasification reaction comes from. Much of the fixed carbon in a gasification would end up being the biochar. So as such, if you remember from the last class, is that when we are doing biomass gasification, of course the synthesis gas is a major product, but we also tend to produce some amount of biochar, and this is fixed carbon is where the biochar is coming from. Then there could be ash and then the moisture content. Further, you would see there is a mismatch between the higher heating value reported in the proximate and the ultimate analysis as well as in both the cases. Well, you can synchronize this difference because the above values are on the as received basis, which means the biomass composition or the LHU and HHU is taken based upon the ash and the moisture content as such, whereas the lower values on a dry basis, which means 15% moisture has been removed for well quantifying the lower value. So that is where the difference is coming from. Then let us now look at the scales of production from this kind of production pathway. We need to understand that when we are talking about biomass, this is basically having a very low density, which also entails that this cannot be transported over long distances. There would be certain times of the day when the biomass is getting harvested, so it might not be available at our own whims. So there would be some harvest seasons along with the biomass production is going to be tied up, and it has to be stored for the remaining part of the year, which entails that I cannot have very big hydrogen production plants. And in this case, the production capacity that I am aiming for is roughly 3,500 tons per day of production capacity, and that is on the as received basis. I remove roughly 15% moisture from it. It is around 3,000 tons per day. Further, I can remove ash from it, which basically means dry and ash free basis. So when I say a term like DAF, which is dry and ash free basis, so this is even lesser, and this would entail that I would also need a good quantity of oxygen because I am not aiming for air gasification, because air gasification, as we have understood in the last class, would mean that there is going to be significant amount of nitrogen in the gas, and then that needs to be cleansed downstream. So better than removing 50% of the the gas composition as nitrogen, it is always advisable why would you let nitrogen enter the system altogether, and that is why we are aiming at oxygen that is getting utilized directly. So this kind of gasifier would have an oxygen composition or oxygen requirement of around 58 tons per day, and the hydrogen production that entails from this kind of system would typically be of the order of 67.79 kilotons per year. And this is significantly lesser than the scale of 370 kilotons per year, which we have been envisioning for charging 40,000 cars a week. So I'm just making you aware of the scales. So this is one of the typical scale that I can reasonably work at. Going beyond this scale would have supply chain issues, or the availability of biomass might be stopped because we might not have so much of biomass in the vicinity. So one thing to understand here is, like, biomass based plants for production of hydrogen or any kind of fuel or chemical would be limited by scale, because the availability of biomass and the transportation of biomass over long distances is a big issue. Further, now this kind of process is also going to produce a significant amount of waste heat, which could be used for in-plant operation, and much of it could be exported as well. So for the plant that I am aiming for, which is producing 67.79 kilotons of hydrogen and using 3,500 tons of biomass on a daily basis, would have a heat production capacity of around 65 or 66 megawatt, and a good amount of it is going to be used in-house. This is going to be used for the biomass handling, the low hoppers, the rectisol unit, which is going to clean up the syngas, which is going to have significant tars, and these tars are basically liquidy compounds, which is a consortium of maybe more than 200 compounds, all higher molecular weight compounds, and this is a problem for the downstream operations. Then you also need a fuel gas compressor, a steam cycle for producing continuous steam to be used in this gasifier, but the major amount of energy are going to be utilized by this air separation unit, which is going to produce this pure oxygen for the operation. And further, I would also need an oxygen compressor to make the plant in sync with the output hydrogen pressure that I would want to work at. So as such, I am going to roughly utilize half of the excess energy within the plant itself, but there would be still a significant amount of energy that is used for other purposes. In this case, this is roughly of the order of 38 to 39 megawatt. So now let us go to Excel sheets and do a similar calculation for biomass based system as we have done for other systems. Okay. So what you see here is a typical sheet, and we have given you the capex for this kind of plant. So you can see the capex for even a small plant like this could be somewhat significant. So for the production capacity of around 67 kilotons of hydrogen per year, I might have to employ a plant with the capex of around $1,200 million or so. Then this kind of plant is expected to take 3 years of construction, and then it's going to operate for another 20 years, and the discount rate for the evaluation is 10%. So this gives me the return on capital of 14.6%, and if I multiply this with the capital expenditure, I am going to spend roughly $177 million a year. Then what also entails are the different kinds of operating costs. Something of significance would be the labor that is employed. That is taken as 1% of the capex investment. So it's 1% of the $1,216 million that is invested in the initial part of the plant. Then 3% as maintenance, 1.5% as insurance, another 1% as catalyst. So adding the 4 gives us the total fixed cost. Then comes in the feedstock. So the feedstock that is assumed in this case is 1 million tons of biomass getting utilized every year. And we have taken a nominal cost of biomass feedstock as $10 a ton. So this is inclusive of the transportation and storage. So although the biomass in some cases might be available for free, the storage and the transportation add significant cost to the biomass supply chain, and that is something we need to be careful about. So in this case, the biomass feedstock comes out around 10 million tons. So the feedstock as such is not very much. And then if I talk about the total annual cost, this is basically an addition of the capital expenditure, the fixed cost, and the feedstock cost. Then in this case, I am also going to produce significant excess energy in the form of electricity. So as we have discussed in the last slide, there could be an excess electricity of the tune of 38.69 megawatt. and if I am able to use this plant for 24 hours and 340 days, this is the amount of electricity that I can generate and can use for other purposes. Again, I am taking a nominal price of electricity as in the previous case studies as $50 per megawatt hour. This gives us a revenue of around $15.79 million a year. For calculating the net cost, what I am doing is I am just adding this total annual cost and subtracting from it is the byproduct electricity. I divide that with the hydrogen production, which happens to be 677 kilotons a year, and this brings in the hydrogen production cost of roughly $3,700 a ton, which is equivalent to roughly $3.7 a kg. And this is somewhat very expensive as compared to the fossil fuel based hydrogen production, but it happens to be somewhat lesser if I compare this with the electrolytic hydrogen production, which was roughly near $4 or so. So if I talk about biomass based hydrogen production, this is going to have somewhat of a cost advantage as compared to electrolytic hydrogen. Again, what I can also do is I can calculate this cost on the basis of dollars per gigajoule, divide this by 120, and this is around $30 per gigajoule. So again, some cost advantage as compared to electrolytic hydrogen, but again way costly as compared to the cost that we have from coal or natural gas based hydrogen production. Again, we can also do a sensitivity analysis as we have done in the earlier cases. So what we can take is like the change in the discount rate, which can vary from, or the return on capital 10 to 25%. And then another thing that is very sensitive in this case is the biomass feedstock cost, which might vary from $5 to $20 based upon the seasons and the availability of biomass. So what we can do again is make a pivot table as we have done in the earlier cases. What if analysis, data table. So in the row cell, I need to enter in this. In the column cell is the feedstock cost, and this is what we have. So currently we are in here. So even if the feedstock cost was to be very less as $5, almost half, the end result would not be much reduction in the hydrogen production price, because not very sensitive to the feedstock price. So as such, it's going to be very like somewhat expensive as compared, but we can see there could be significant impact on the return on capital. So in case we are able to build the plant in a smaller time, or we could have like lesser discount rate available or applicable to such kind of investment, this can help us bring down the cost of hydrogen production from biomass. So what we can do next is try to understand the different kinds of business models or the production of hydrogen from the different routes. So let us try to have a brief summary of the hydrogen production at different scales and from different routes. So what you have is a table basically bringing down the different hydrogen production routes that we have been discussing in the previous classes. So the routes that we have primarily discussed is the gas based production or natural gas production, either through the methanation or the PSA route, the coal based production from PSA and methanation. Then for the sake of clarity, we have also added in what if we have gas based production but at a smaller scale. So the scale has now been reduced from 300 to 150 to much lesser 26.2 and way lesser around 1.76 kilotons of hydrogen per year. So this is a very small scale operation. So the scale for the gas of course remains at 373 kilotons per year. It is way more for coal based production, because coal based production processes tends to benefit from the economy of scale, and you would normally not work at coal based hydrogen production at a smaller cases. It's quite opposite for the biomass based production, where you would be working with very small amount of biomass coming from the supply chain issues. The next thing is the capex. So the capex you can see is somewhat similar to the earlier cases. For the small case, the capex have been decreasing, taking into account the economies of scale. The construction period is almost 3 years for all the plants. Only the coal based plants have 4 years construction period. Then the plant life for smaller plants tends to be lesser, maybe of the order of 15 years, whereas for the plants which are beyond 300 kilotons, I am assuming 20 years. Based upon the plant life, the construction years, as well as the 10% discount rate, the ROCs are given in here. You multiply the ROC with the capex and add to it the different kinds of operating and labor expenses. This is what you get in the non-gas operating expenses that I have done for you. You guys can check it at your own end. So this is an exercise that you can do for enhancing your understanding of this particular kind of analysis. Then of course we would have the feedstock usage increasing as we have an increased production of biomass. And further, we have also taken in the feedstock cost of around $2 per gigajoules for the gas. And for the coal and biomass, we have assumed to be on a lesser front. And we are also giving the feedstock cost, and then there could be different kinds of byproduct credit that entails. So this could be quite huge for natural gas based facilities. In coal, you don't have much of it, majority of it comes from sulfur, and in again there could be significant coming from biomass as well. Then to make the comparison interesting, let us also bring in the element of GHG emissions. So these plants are going to emit different quantities of greenhouse gases. So of course this would be maximum for the coal based plant, because the coal based systems happen to be the most carbon intensive, but we would also have significant CO2 coming from the natural gases plants as well. So if I provide a cost of $50 per ton for this CO2, I would have the following costs that are appropriate for sequestering this amount of CO2. And this is something that I would like to add to the production cost, which I have done. And based upon this production cost, I can divide this by the hydrogen production rate to get the hydrogen production values. So this is the dollars per ton of hydrogen production values if I am also taking in the cost for CO2 sequestration, and in this case I have taken a nominal value of $50 per ton of CO2. However, we need to understand that this value could be somewhat higher if we are sequestering dilute CO2, but in this case I am assuming that majority of these plants would be partial oxidation based, and the sequestration can come from like benign technologies which are able to sequester CO2 at around $50 a ton of CO2. And then for the sake of comparison, we can also have the non-GHG cost as we have been calculating in the earlier cases. For comparing this with electrolytic hydrogen production from electrolyzers, since these kind of costs are very sensitive to the price of electricity, I have given in two costs. One at which the electricity is available at $50 a megawatt hour, and the other one in which the electricity is available at $25 per megawatt hour. So the entailing price of hydrogen from these two facilities would be around $4,000 and $2,500 per ton, or around $4 per kg and $2.5 per kg. Let us want to compare these options for so called low carbon hydrogen. So if I have this hydrogen production from other pathways, we see that the natural gas production almost takes a lead in almost all the scales. From the low scale to the high scale, we see that like it is always beneficial to go with natural gas based hydrogen production, because even in taking the carbon sequestration price, this happens to be much more economical at the current electricity prices. Of course, if we are able to reduce the electricity production price to $25 a megawatt hour at a very small scale, this might become comparable with the natural gas based case, but in most of the cases not much benefit can be seen from electrolytic hydrogen production. Further, the coal based cases might happen to be a bit expensive, but still happen to be way cheaper than electrolytic hydrogen at the scales they are operating at, even after taking into account the carbon sequestration. But some of you might have guessed that there is a problem with this calculation. The problem is that I have taken a price of feedstock that is uniform. And what we have discussed in the previous classes is the smaller the size of the facility, the greater is the price of this feedstock. So if we try to adjust this feedstock price based upon the scale, we might have a slightly different story to tell. So again, this is the same table essentially with the same kind of comparison, but what I have done here is updated the feedstock price to something that you are going to find much in reality. So the smaller the size of the plant is going to be, the more expensive it is going to buy the natural gas for this kind of plant. And other analysis remain the same, and what we finally have the final hydrogen cost taking into account the carbon sequestration as well. So what we find here is, if we are talking about a very small scale at which the natural gas is available at a premium, it might be worthwhile to use electrolyzer as of today, because that happens to give you cheaper hydrogen. And this happens to be true even in case I am working with slightly higher scale of around 26.2 kilotons, and if I am able to get a cheaper electricity, the electrolyzers might take a lead. But beyond 150 kilotons a year, it's going to be cheaper to go by natural gas based hydrogen production, even when the gas is available at a slight premium of around $4 per gigajoule or lesser. Something similar can be said for coal based hydrogen production as well. So even as of today, it happens to be cheaper as compared to electrolytic hydrogen. But we need to understand that in case there are some kind of geopolitical events which basically affect the prices of this gas or coal, the story could be other way around. Again, comparing this with biomass, we can say that the biomass based hydrogen production is somewhat comparable to electrolytic hydrogen production, and as of today biomass based systems might have a slight edge as well as the economics is concerned. So to summarize the conclusions from this analysis, we would like to say that, like, if I want to compare electrolytic hydrogen production from other pathways, we find that electrolytic hydrogen does tend to have an edge as far as the small hydrogen production is concerned. So if the scale is around 1 kilotons a year, possibly it's advisable use electrolysis, and this is what has been seen in the past as well. So like industries which had a small use of hydrogen, a typical example would be the dalda industry or the oil industry that or the cooking oil that you have been eating in the past, normally employed electrolyzers because it was cheaper to produce hydrogen through these electrolyzers rather than using steam methane reforming, which is applicable at a large scale. Then if I am talking about large scale hydrogen production, possibly at the scale of more than 150 kilotons or so, steam methane reforming tends to have an edge, and but this is based on the premise that the gas is available at a steady rate and at a nominal price. So of course the price would increase to around $4 or $5, but beyond that, if there is a price of increase of maybe more than $5 per gigajoule, there could be heavy repercussions, and the electrolytic route then might have an advantage. And so the electrolytic route would have a cost advantage where in the areas which have a very high gas prices. So in the future, when we see that the gas reserves are slowly getting dried up, we might come across a scenario where electrolysis might be the suitable route. Further, if I am talking about coal and biomass based hydrogen, of course for the coal we need to have a certain economy of scale to make it applicable. So coal based plants would normally want to work at significant scale, and at scale they might be able to give a good economics along with carbon sequestration, and something similar for biomass. So biomass would be the opposite, wherein we have a scale limitation, but the cost as of now would be somewhat similar to electrolysis. So this is something that might change if there are electrolytic research that increases and the price of electrolysis and the electricity comes down in the future. So with this, we have tried to give you a synopsis of how the different technologies are going to compare among themselves as well as hydrogen production is concerned. And with this, we take a break from the current class. Thank you.